Okay, here we are. We're going to do some net ionic equations today. Actually, we're going to learn about solubility rules. We're going to learn about ionic equations and then net ionic equations. It's a pretty important concept. Good news is no math involved. Bad news is there's a bit of memorization you're going to need to take care of. Now we're going to do several demonstrations in a huge lab that deals with these net ionic equations and learning your solubility rules. So there are a set of rules here in your notes that you have to learn. They're really not that bad. I'm going to give you plenty of opportunity to learn them by giving you lots and lots of examples in class, in lab, and of course for homework. Let's go through those very, very quickly. Number one, every ionic compound that contains an element from group 1, like lithium, sodium, potassium, those compounds will be soluble, and ammonium compounds are also soluble. There are no exceptions to that rule. Acetates and nitrates are always soluble, and there are no exceptions to that rule. So, for instance, if I had potassium chloride, I would expect that to be soluble because it has potassium in it. If I had silver nitrate, I would expect that to be soluble because it has a nitrate in it, and there are no exceptions to those first two rules. Then chlorides, bromides, and iodides are soluble, but we have a few exceptions here. Basically, those exceptions are silver, mercury, and lead. So if you have silver, mercury, or lead chloride, they will not dissolve in water. Silver, mercury, and lead bromide will not dissolve in water. Silver, mercury, and lead iodide will not dissolve in water. But all other chlorides, bromides, and iodides would be expected to be soluble in water. Sulfates are soluble in water. So, for instance, potassium sulfate would be soluble in water. Copper 2 sulfate would be soluble in water. But there are a few exceptions. Calcium, strontium, barium, and then our friends up above, silver, mercury, and lead sulfates are insoluble. Now, the next couple of rules, let's see, the next three rules are pretty much the same. We have carbonates, phosphates, and sulfides. They are insoluble. Now, there are some exceptions to that, as you would expect. If we have a carbonate, phosphate, or a sulfide that has something from group 1 in it, of course it would be soluble, because we said earlier everything in group 1 is soluble without an exception. And ammonium, carbonates, phosphates, and sulfides we would expect to be soluble. And the last rule is the hydroxide rule. Most hydroxides are insoluble. Now the exceptions are similar to those above, except we're going to add calcium, strontium, and barium. Those actually would be soluble along with members of group 1. For instance, lithium, sodium, potassium, cesium, and rubidium hydroxide would be soluble. Calcium, strontium, and barium hydroxide would be soluble, but the other hydroxides are not. Now what we're going to do here, and you'll see this demo in class, and you can also see the YouTube demo where I do a net ionic reaction for you, so just check out my YouTube channel for that. But we can take two solutions. We can take lead nitrate, and according to our solubility rules, nitrates are soluble. So if we have a solution of lead nitrate, we would expect the lead nitrate, of course, to dissolve in that water. And we'll take sodium iodide. Once again, sodium's in group 1. We expect sodium compounds to be soluble. So we have lead nitrate and sodium iodide. What happens if we mix them together? Well, that potentially we might be able to get something created that's insoluble. So we could have a double replacement reaction. The sodiums and nitrates, they can potentially get together. But according to our solubility rules, those are soluble. So we wouldn't expect a solid to form here because all sodiums are soluble, or we could use the nitrate rule which says all nitrates are soluble. But can't lead and the iodide get together? And we could form PbI2, which is insoluble according to our solubility rules. Remember, iodides are soluble except we have lead iodide that is insoluble. So if we mix these two solutions together, we would expect something called a precipitate to form, or a solid forming in solution. It would turn cloudy. It would be a suspension. The particles would eventually settle to the bottom of the beaker. Okay? Now, let's use that to help us write molecular, ionic, and net ionic equations. Now we're going to have to use our solubility rules for part of this. Now first of all, let's take sodium chloride and silver nitrate. You need to know how to write formulas in this class. Sodium chloride is NaCl, and we'll dissolve that in water, and silver nitrate, AgNO3, also dissolved in water. Now all of these are going to be double replacement reactions. So the sodium and the silver are going to switch partners. Now sodium's positive 1, nitrate's negative 1, we will form NaNO3. Now I'm not going to put AQ there yet, we're going to wait and we'll fill that blank in just a minute. Silver and chloride could get together. Silver's 1 plus, chloride's 1 negative, and that would form AgCl. We'll also leave that blank for just a moment. Well, that moment didn't last that long. Let's find out what we put there. If these are soluble in water, according to our solubility rules, we will put AQ. If they are insoluble, we will put an S, meaning they form a solid in solution. So for sodium nitrate, we can use rule number 1 or 2. Sodiums and nitrates are always soluble, and there are no exceptions. So I will put an AQ here. Well, what about silver chloride? Well, we have to use our chloride rule, our chloride, bromide, and iodide rule. It says most are soluble, except, look, silver chloride's in that exception. That means it will not be soluble in water, so we will put an S after that, meaning it forms a solid. We'll quickly check to make sure that's balanced, and it is. Now, ionically is how these particles actually exist in water. Remember, for ionic compounds that are soluble, water can split up the ions. It surrounds them and separates them from each other. So ionically, when these are in water, we really have sodium ions and chloride ions separated from each other. We have silver ions and nitrate ions that are separated from each other. On the other side, since that's AQ, these are also separated from each other as ions in water, Na plus and NO3 negative. However, when we have a solid, water cannot separate them. They are more attracted to each other than they are to water. So we leave those stuck together. So we have our ionic equation. Now notice we have some of the same species on both sides of the equation. For instance, Na plus and Na plus, NO3 negative and NO3 negative. Those are called spectator ions. They're really not participating in the reaction. They're the same before and after. So we can cross the spectators out. And whatever we have remaining, we have what's called the net ionic. Now when I write the net ionic, I like to write the positive ion first. So I have Ag plus AQ remaining on the reactant side, and Cl negatives AQ. On the product side, I have AgCl solid, and that is my net ionic equation. Okay, it's what I have left after the spectator ions have been crossed off. Okay, let's do another one for practice, okay? Let's do potassium carbonate and calcium bromide. Potassium carbonate is K2CO3 AQ, and just by the way, your reactants are going to all be AQ. We can check our solubility rules to verify it, but trust me on this one. Calcium bromide is CaBr2 AQ. Double replacement, potassium's positive 1, bromide's negative 1, KBr is formed. We'll leave that blank for a moment. Calcium's 2 plus, carbonate's 2 negative, CaCO3 is formed. Now let's quickly find out what goes in these blanks. Potassium bromide. Let's use rule number 1. Potassium ions are soluble, no exceptions. So that's a potassium compound. We will put an AQ after that. It means it dissolves in water. What about calcium carbonate? Well, here's our carbonate rule down here. It says carbonates are insoluble. Now, there are a few exceptions. Let's see if calcium's one of them. Group 1? Nope, calcium's in group 2. And ammonium. Okay, calcium's not an exception here, so it's insoluble. So we put the letter S there, meaning that it will form a solid in water. Let's balance this quickly by putting a 2 in front of KBr. That gives me 2 potassiums and 2 bromines on both sides. Okay, ionically, let's split these guys up. When this splits up in water, I have 2 potassium ions that separate from my carbonate ion, which is 2 negative. I have a calcium 2 plus ion that separates from my 2 bromide ions. So Br2 splits up into 2 bromide ions. This is AQ, so my 2 potassium bromides split up into 2 K pluses and 2 Br negatives, surrounded by water. Now what do I do with this solid? Well, remember, they are more attracted to each other than they are to water, so they stick together. I do not dissociate them. Do I have any spectators present? Look carefully. You bet. 2 bromides and 2 potassiums. Whatever's left over is my net ionic. I like to write the positive ions first, so calcium 2 plus AQ and CO3 2 negative AQ react to form CaCO3 solid. So that is my net ionic reaction between potassium carbonate and calcium bromide. Okay, let's do another one. Let's do copper 2 sulfate and barium nitrate. By the way, have you noticed how important it is to be able to write formulas? If you can't write formulas, you need to get in for that help or review your notes from earlier in the year. Copper's 2 plus, sulfate's 2 negative, so that's CuSO4. Barium nitrate, barium's 2 plus, nitrate is 1 negative, so that's BaNO3 in parentheses with a 2. Double replacement, so copper and nitrate will potentially get together. Remember, copper's 2 plus, nitrate's 1 negative, so that's CuNO3 We'll leave the parentheses blank for just a minute. And barium and sulfate. Barium is 2 plus, sulfate is 2 negative, so that would be BaSO4. Okay, let's check our solubility rules. Have you learned any yet? For instance, do you know the nitrate rule? Because copper stuck to it here. Nitrates are soluble. Oops, sorry, I looked at the wrong one. Nitrates are soluble and there are no exceptions. So I can put an AQ after copper 2 nitrate. But the sulfate rule, we'd better look at pretty carefully. It says sulfates are mostly soluble. That means some are not. Do you see how barium sulfate is an exception? That means it is not soluble. So barium sulfate is my solid. Ionically, we'll split these guys up. Copper 2 plus AQ and sulfate AQ, so they dissociate from each other. Barium 2 plus dissociates from those 2 nitrates. On the product side, copper 2 plus will dissociate from those 2 nitrates, and barium sulfate sticks together. They are more attracted to each other than they are to the water, so they are insoluble. Take a look. Do we have any spectators? You bet we do. 2 nitrates and my copper 2 plus. Whatever's left over is my net ionic. Barium 2 plus, AQ, SO4 2 negative, AQ, forms barium sulfate solid. That is my net ionic equation. So when I mix these two solutions together, I would expect to see a cloudy substance form, and that would be my barium sulfate. Okay, let's do one more. We'll try to do it quickly. This one's interesting. Chromium 3 iodide. That's Cr(I3)AQ, and ammonium acetate. NH4 and acetate is C2H3O2 negative 1. That's soluble. Double replacement. Chromium and acetate will get together. Now chromium's 3 plus and acetate's 1 negative. So it's CrC2H3O2 in parentheses with a 3 on the outside. We'll fill in the parentheses in just a sec. And ammonium and iodide get together. Ammonium's 1 plus, Iodide's 1 negative, so it's NH4I. Okay, let's find out if these are soluble. There's no chromium rule, but there is an acetate rule. It says all acetates are soluble, no exceptions. So this is AQ. Ammonium iodide. Have you learned the ammonium rule yet? All ammoniums are soluble, no exceptions. AQ. Interesting. Both products, both reactants are AQ. I wonder what the ionic equation is going to look like. Let's balance this quickly. We're going to put a 3 here and a 3 there to balance that. So ionically, I have Cr3 pluses, AQ, and 3 I negatives when they dissociate from one another. I have 3 ammoniums and 3 acetates. On the product side, these are AQ, so these dissociate, chromium 3 plus, and my 3 acetates. I'm running out of room here. And these dissociate as well, they're also AQ. So I have 3 NH4 pluses, and I have 3 iodides. Do you think we have some spectators here? Absolutely. 3 iodides are gone. The 3 ammoniums are gone. The 3 acetates are gone. And the chromium 3 pluses are gone. Everything cancels out. What does that mean? What reacts in this reaction? Well, when we end up with a situation like this, we simply write the letters N, R. And this stands for no reaction. So, if we mix these two solutions together, would anything happen? No. We have ions before, we have ions after. Nothing reacts to come together, so we say NR, or no reaction. Now, a special note here, if you know your solubility rules well, you can usually skip directly to the net ionic, unless, of course, the others are requested. So, if you get good at this, you can look at the instructions, what's reacting together, and if you know how to write formulas and you know your solubility rules really, really well, you can usually skip right to the net ionic, unless, of course, I ask for the other two on your homework. Okay? All right, we'll demo this in class, and we're also going to do a big lab. We're going to have about 50 different combinations that we'll be mixing together, and you have the chance to write about 50 different net ionic equations. It'll be lots of fun. And I'll demo that lab for you coming up on YouTube. So enjoy. Have a great day.